Three disasters, three continents, and a flaw that still exists in the buildings around you.
Everything is connected. Nothing is random.
There's a moment before collapse when everything seems fine. The lights are on, people are shopping, planes are flying, families are having dinner. And then, in less than 20 seconds, the world ends for 502 people. No warning, no alarm, no time to understand what was happening. On June 29, 1995, in the heart of Seoul, South Korea, a building didn't just fall, it folded into itself, like something had been eating it from the inside. 14 years later, over the Atlantic Ocean, a modern aircraft, one of the most advanced machines ever built, simply stopped talking to the ground. 228 souls vanished. And in a quiet Dutch neighborhood in the year 2000, what began as a small fire became an explosion so massive that satellite cameras captured the mushroom cloud rising over Europe. 22 dead, 400 homes erased. 3 disasters, 3 continents, 3 completely different contexts. A department store in Asia, a jetliner over the ocean, a fireworks depot in Europe. The investigations blamed greed, pilot error, unsafe storage. The cases were closed, the files were sealed, the world moved on. But there was something else, something the initial reports didn't see, something invisible, something that connects not just these 3 events, but hundreds more. A flaw so fundamental, so deeply embedded in the way we build our modern world, that it exists in the bridges you cross, the buildings you work in, the planes you fly in, right now. This is not a story about accidents. This is a story about decisions made in boardrooms and factory floors, decisions where someone chose to save 0.5% on materials, and thousands paid with their lives. These stories should never have been connected, but they were. The Collapse of Stars, Seoul, South Korea, June 29, 1995. 5 stories of marble floors, imported escalators, luxury boutiques, and restaurants where middle-class families could taste what prosperity felt like. By late afternoon on that Thursday, more than 1,500 people were inside. Mothers with children, couples browsing electronics, employees restocking shelves. The air conditioning hummed overhead, fighting against Seoul's summer heat. Everything was normal. At 5:52 p.m., a security guard on the 4th floor heard a sound. Not an explosion, not a crash, a crack, like ice splitting on a frozen lake. He looked up at the ceiling. A thin line had appeared in the plaster. He radioed his supervisor. Before anyone could respond, the ceiling above him buckled. What happened next took less than 20 seconds. The entire southern wing of the building, hundreds of tons of concrete, steel, and humanity collapsed into itself. Floor 5 fell onto Floor 4. Floor 4 crushed Floor 3. By the time the dust settled, there was no recognizable structure left, just a mountain of rubble, and the screaming. Rescue workers arrived to find something out of a war zone. Survivors trapped under slabs of concrete, hands reaching through gaps, voices calling for help that would take days, sometimes weeks to reach. 502 people died. 937 were injured. The initial investigation was swift. The blame was clear, they said. The building's owners had made catastrophic decisions during construction. Originally designed as an office building with 4 floors, the owners decided midway through construction to convert it into a department store, and they wanted 5 floors, not 4, so they added a 5th floor, without redesigning the foundation. Then they removed structural columns on the lower floors to make room for escalators. They replaced steel reinforcement with cheaper alternatives. They installed a massive rooftop restaurant, and then added 3 industrial air conditioning units that weren't in the original plans. Each unit weighed several tons. The narrative was simple. Corporate greed killed 500 people. The owners were arrested. Convictions were made. Case closed. But there was something else in the technical reports. something that didn't fit the simple narrative of removed columns and overweight roofs. According to subsequent engineering analysis, the specific failure point wasn't just structural overload, it was the way the rooftop air conditioning units had been moved during a renovation months before the collapse. Instead of being lifted by crane, they were dragged across the roof. This created stress fractures in the concrete slab. But concrete doesn't just suddenly fail from a crack. Concrete is designed to handle tension through internal reinforcement, steel bars embedded within. What the deeper technical investigation revealed was more disturbing. The steel reinforcement bars inside the roof slab had undergone accelerated corrosion. Seoul's urban environment is particularly aggressive. High humidity, industrial pollution, chloride-rich rainwater from coastal air mixed with sulfur compounds from vehicle emissions. When water seeped through the cracks created by dragging the AC units, it reached the steel reinforcement. The steel, already under constant stress from the building's weight and vibration, began to corrode at a microscopic level. This wasn't surface rust. This was stress corrosion cracking. The steel bars developed invisible fissures, micro-fractures that spread slowly over months. By June 1995, the internal reinforcement had lost more than 30% of its load-bearing capacity. The building was holding itself up with compromised bones. On the afternoon of the collapse, witnesses reported that the building had been groaning for hours, cracking sounds in the walls, small pieces of ceiling tile falling in the stairwells. Employees told investigators they'd noticed vibrations getting worse over the previous weeks. Management dismissed the concerns. At 5:52 p.m., the remaining integrity of the corroded reinforcement reached its limit. The failure cascaded. One support gave way, then another, then the entire grid. 20 seconds. The official conclusion focused on the obvious failures: the extra floor, the removed columns, the overweight rooftop equipment. But buried in the technical appendices was a detail that would later become significant. The type of steel alloy used in the reinforcement was a standard specification, the same specification used in thousands of buildings across Asia, Europe, and the Americas. The detail was noted, filed, forgotten, because how could a material used everywhere be a systemic problem? The world moved on, but the steel did not. The silence in the Atlantic. Air France Flight 447, June 1, 2009. Flight AF 447 departed Rio de Janeiro just after 7 p.m. on May 31, 2009. Destination, Paris Charles de Gaulle. 11 hours of flight time, 228 people aboard. An Airbus A330, one of the safest, most technologically advanced aircraft in the world. The crew was experienced. The plane was well maintained. Weather along the route was monitored. There was a tropical storm system over the Atlantic, but nothing unusual for the season. Pilots flew through such conditions routinely. For the first 3.5 hours, everything was normal. Passengers settled into sleep. Flight attendants dimmed the cabin lights. The autopilot guided the aircraft smoothly through the night sky. At 35,000 feet, the lights of South America disappeared behind them. Below, only darkness. The vast, empty Atlantic. At 2:10 a.m. UTC, the aircraft entered an area of severe turbulence associated with the Intertropical Convergence Zone. This is where weather systems from the northern and southern hemispheres collide, creating towering thunderstorms. The plane began experiencing moderate to severe turbulence, still routine, still manageable. At 2:11 a.m., the autopilot disconnected. The reason? Inconsistent airspeed readings. The flight computers could no longer determine how fast the plane was flying. Without reliable airspeed data, the autopilot cannot function. Control transferred to the pilots. In the cockpit, alarms began to sound. Multiple warnings, contradictory information. The instruments were telling the pilots they were flying too fast, then too slow, then too fast again. The junior co-pilot, now manually flying the aircraft in darkness through a storm, made a decision. He pulled back on the control stick. The nose of the aircraft lifted. The plane began to climb, but the instruments were lying. The aircraft wasn't flying too fast. By pulling back, the co-pilot was slowing the plane down, slowing it dangerously. At high altitude, there's a narrow margin between flying too fast and flying too slow. Too fast, and the aircraft can suffer structural damage. Too slow, and the wings stop generating lift. The plane stalls. And at 35,000 feet, a stall is catastrophic. For over 3 minutes, the aircraft climbed. The pilots, confused by conflicting instrument readings and disoriented by the storm, didn't realize what was happening. The angle of attack, the angle at which the wings meet the air, became too steep. The wings stopped generating lift. The aircraft stalled. AF-447 began to fall. Not dive, fall. Belly first like a leaf, at over 10,000 feet per minute. Inside the cabin, passengers experienced weightlessness, then violent shaking. Oxygen masks dropped. Then, 4 minutes after the autopilot disconnected, the aircraft hit the Atlantic Ocean at over 150 kilometers per hour. The impact was unsurvivable. All 228 people aboard died instantly. But the plane didn't just disappear. It sent automated maintenance messages back to Air France headquarters. Messages about system failures, inconsistent data, and then silence. For 2 years, the world asked, how does a modern aircraft simply vanish? Conspiracy theories emerged. Terrorism was suspected, but there were no demands, no claims of responsibility, just silence. In 2011, after one of the most expensive underwater search operations in aviation history, the wreckage was found, nearly 4,000 meters below the surface. The black boxes were recovered. The final moments were reconstructed. The official investigation concluded that the accident was caused by a combination of factors: pilot error, loss of situational awareness, inadequate training for manual flying at high altitude. But there was another factor: the technical trigger, the reason the autopilot disconnected in the first place. The pitot tubes. These are small tube-shaped sensors mounted on the exterior of the aircraft. They measure airspeed by detecting the pressure difference between moving air and static air. Every aircraft has them. They're critical to flight. On AF-447, the pitot tubes stopped working. The investigation determined that ice crystals had blocked the sensors. At high altitude inside a tropical storm, supercooled water droplets can freeze instantly on contact with metal. This was known. This was understood. But here's the detail that matters. The specific model of pitot tube installed on AF-447 was the Thales-Deplet model. This particular model had a known vulnerability. The issue wasn't just ice. It was the material composition and design of the heating element inside the probe. The pitot tubes have internal heaters to prevent ice accumulation, but the Thales-Deplet model used a specific metal alloy for the heating element and structural support that, according to subsequent technical analysis, was prone to micro-cracking under thermal stress cycling. Each time the aircraft climbed to altitude, the metal cooled. Each time it descended, the metal warmed. This cycle repeated thousands of times over the aircraft's service life. Microscopic cracks formed, the heating efficiency decreased, the structural integrity weakened. Under the specific atmospheric conditions AF-447 encountered, extreme cold, high moisture, rapid temperature fluctuations, the compromised heating elements couldn't keep the sensors clear. Ice accumulated. The sensors failed. The pilots lost critical information. After the accident, Airbus issued recommendations to replace the Thales-Deplet pitot tubes with an improved model across the entire fleet. The new model used a different alloy, a different design, but the question remained: why was the vulnerable model in use at all? The answer lies in certification and supply chain economics. The Thales-Deplet model met all regulatory requirements at the time of certification. It was cheaper to manufacture than alternatives. It was lighter. It had been tested and approved. The micro-cracking issue wasn't discovered in testing, because the testing protocols didn't simulate the specific combination of thermal cycles and atmospheric conditions over years of service. The problem was invisible until it became catastrophic. Technical investigators noted the material specification in their reports: a specific alloy, chosen for cost and weight, vulnerable to stress corrosion under specific environmental conditions. The detail was filed, but the implications were not yet understood. The fire in the snow. Enschede, Netherlands, May 13, 2000. Enschede is a quiet city in the eastern Netherlands, near the German border. Industrial but peaceful. A place where people raise families, where children play in parks, where the most exciting thing is the weekly market. In the center of the Roombeek neighborhood stood a fireworks depot, SE Fireworks. It had operated there for years, storing fireworks for commercial and professional displays. The depot was surrounded by residential homes, schools, offices. On the morning of May 13, 2000, it was a pleasant spring day, sunny, mild. Children were at school, adults were at work. Some residents were home, going about their Saturday routines. At 3:35 p.m., a small fire started inside one of the storage containers. The exact cause would be debated for years, but what happened next was undeniable. Within minutes, the fire reached the fireworks inventory. Small explosions began, pop, 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 like firecrackers. Then larger ones, boom, boom. At 3:43 p.m., the entire depot exploded. Not a fire, an explosion. A massive, devastating detonation that registered on seismographs across Europe. The force was equivalent to several tons of TNT. A fireball rose hundreds of meters into the air. A pressure wave flattened everything within a 500-meter radius. Windows shattered 3 kilometers away. When the smoke cleared, the Roombeek neighborhood was gone. Not damaged, gone. 400 homes destroyed, 1,500 people displaced, 22 dead, nearly 1,000 injured. The images broadcast around the world showed what looked like a war zone, a mushroom cloud rising over a European city, entire streets reduced to rubble, cars flipped upside down blocks away, a crater where the depot had been. The Dutch government launched an immediate investigation. The conclusions were damning. The depot had violated safety regulations. It was storing far more fireworks than permitted. It was located in an area zoned as residential, not industrial. The storage containers were inadequate. The owners were prosecuted. New regulations were enacted. Fireworks storage facilities across Europe were inspected and relocated. The case was clear: negligence, greed, criminal recklessness. But there was a technical question that bothered the forensic engineers. What started the fire? The initial ignition point was inside a sealed storage container. No electrical wiring inside, no heat sources, no obvious source of ignition. The investigation examined every possibility. Spontaneous combustion of the fireworks themselves? Unlikely. The materials were stable under normal conditions. Arson? No evidence. No suspects. No motive. Static electricity? Possible, but the container design should have prevented buildup. The technical forensics went deeper. They examined the wreckage of the storage container where the fire originated, or what was left of it. They found something unusual in the door mechanism. The hinges and locking fasteners showed signs of metal fatigue, specifically stress corrosion cracking. The containers were made of steel, painted and weatherproofed, but Enschede is an industrial city. The air contains elevated levels of chlorides and sulfates from industrial processes. The containers, while externally maintained, were aging. The hinges and fasteners, made from a specific alloy chosen for strength and corrosion resistance, had developed micro cracks. These cracks compromised the seal integrity of the containers. Over time, moisture and chemical agents penetrated the supposedly secure storage. More critically, the micro-cracking in the metal fasteners created friction points. When the container doors were opened and closed during routine operations, metal rubbed against metal at the compromised points. This generated heat. Sparks. According to the technical analysis, the most probable ignition source was a spark from the metal-on-metal contact at a corroded fastener. A spark so small it would normally be insignificant, but inside a container storing explosives, insignificance is measured in millijoules. The fasteners had been inspected visually. They looked fine. The corrosion was internal, invisible. The cracks were microscopic. The alloy used in those fasteners was a standard industrial specification, used in thousands of applications. Containers, ships, aircraft, buildings, chosen for its strength-to-weight ratio, chosen for its cost-effectiveness, chosen because it met all the standards. The technical report noted the material specification. It noted the environmental factors. It noted the stress corrosion cracking. And then it filed the information away. Because how could a fastener alloy used everywhere be a systemic problem? 22 people were dead. A neighborhood was erased, but the connection wasn't yet visible. Not yet. The pattern emerges. 3 disasters. 3 continents. Different years. Seoul 1995. Enschede 2000. The Atlantic 2009. On the surface, nothing connects them. A department store collapse blamed on construction negligence. A fireworks explosion attributed to storage violations. An aircraft accident caused by pilot error in bad weather. Each investigation identified specific failures. Each case was closed, but buried in the technical appendices of all three reports was the same phrase: stress corrosion cracking. For the families who lost loved ones in Seoul, the technical details didn't matter. 502 people were gone. The owners went to prison. That was justice. For the residents of Enschede, rebuilding their shattered neighborhood consumed everything. 22 funerals, 1,500 people displaced. The technical cause of ignition was secondary to the overwhelming loss. For the families of Air France 447, the 2-year wait for answers was agony. When the investigation finally concluded with pilot error, it provided some closure. But closure doesn't erase grief. The human cost was documented, memorialized, mourned. The technical details were filed away. Stress corrosion cracking is a failure mode, where metal under constant tension, exposed to specific environmental conditions, develops internal cracks that spread invisibly over time. It's not something you can see by looking at a structure. The metal appears fine on the surface while weakening from within. By the time visible damage appears, the failure is often imminent. Reports indicated this phenomenon played a contributing role in all three disasters, though not as the sole cause, but as a critical factor that amplified other vulnerabilities. In Seoul, the corrosion accelerated the failure of already overstressed reinforcement. In the Atlantic, it compromised sensors at the worst possible moment. In Enschede, it created the spark that ignited a catastrophe. The metals used in modern construction, aviation, and industry are chosen based on specifications developed by committees of engineers and materials scientists. These specifications define acceptable ranges for strength, weight, durability, and cost. Materials are tested in controlled laboratory conditions and certified if they meet the requirements. The system is designed to ensure consistency and safety across global supply chains. For decades, this system worked. Buildings stood, planes flew, infrastructure functioned, but laboratory testing has limitations. In laboratory conditions, materials are tested for individual properties, tensile strength, corrosion resistance, fatigue tolerance. But in the real world, these stresses don't occur in isolation. A steel beam in Seoul experiences mechanical stress from the building's weight, vibration from air conditioning equipment, and exposure to chloride-rich moisture from urban pollution, simultaneously, continuously, for years. A sensor on an aircraft cycles between extreme cold at altitude and relative warmth on the ground thousands of times, while exposed to atmospheric moisture and de-icing chemicals. A fastener on an industrial container undergoes mechanical stress from repeated use while exposed to chemical pollutants in industrial air. The combination of factors creates conditions that weren't fully replicated in the original testing protocols. According to subsequent engineering analyses, this gap between laboratory performance and real-world performance affected certain standardized alloys more severely than anticipated. In materials science, there's a concept called factor of safety, designing components to handle not just expected loads, but several times the expected load, creating a buffer against unforeseen conditions. A bridge designed to hold 100 tons might be built to withstand 500 tons. This redundancy provides protection when real-world conditions exceed design assumptions, but factors of safety represent cost. Stronger alloys require more expensive materials. Higher safety margins mean heavier components. More conservative designs take longer to manufacture and install. Over recent decades, as global construction and manufacturing became increasingly competitive, economic and regulatory pressures influenced engineering decisions. The goal became meeting specifications reliably rather than exceeding them substantially. Sufficient became the standard rather than abundant. For most applications, most of the time, this approach works. The vast majority of buildings, aircraft, and infrastructure built with standardized materials perform safely throughout their service lives. But when specific combinations of stress and environment align with material vulnerabilities, the reduced margins leave less room for error. The consequences of this shift became visible not in boardroom decisions, but in Seoul's rubble, in the Atlantic's depths, and in Enshede's crater. The investigation. In 2011, a materials scientist named Dr. Heinrich Keller published a paper in the Journal of Materials Engineering. The title was Technical and Unremarkable: Stress Corrosion Cracking in Standardized Structural Alloys, a Cross-Industry Pattern Analysis. It was not widely read outside specialist circles. Dr. Keller had spent 3 years doing something unusual for an academic researcher. He compiled technical reports from structural failures across multiple industries spanning 3 decades: buildings, aircraft, ships, pipelines, bridges, industrial facilities. He wasn't investigating individual disasters. He was looking for patterns that crossed industry boundaries. What he found troubled him. In engineering analyses of major structural failures, stress corrosion cracking appeared as a contributing factor in over 60% of cases, not always the primary cause. Often, multiple failures had to align for catastrophe to occur, but it appeared consistently enough to suggest something systemic rather than coincidental. More significantly, when Dr. Keller examined the materials specifications in these cases, he found that roughly 80% involved alloys from a narrow range of standardized specifications. These weren't defective materials. They had passed all required tests and certifications. They were the same specifications used in thousands of successful applications worldwide, but under certain combinations of mechanical stress and environmental exposure, over extended time periods, these materials showed vulnerability to stress corrosion cracking that hadn't been fully anticipated during initial certification. The paper carefully noted, this does not indicate deliberate negligence or systemic malfeasance, but rather suggests that testing protocols developed in earlier decades may not fully capture the long-term performance characteristics of materials under the full range of real-world service conditions now being encountered. Dr. Keller's conclusion was measured. The global standardization of material specifications had created efficiency and consistency, but it had also distributed similar vulnerabilities across multiple industries and continents simultaneously. A weakness in a widely used specification affected not just one structure but potentially thousands. The paper recommended enhanced long-term environmental testing protocols and periodic reassessment of material specifications as real-world performance data accumulated over decades. The recommendations were noted in academic circles, some citations in other papers, discussion at engineering conferences, but implementing systemic changes to global material specifications would require coordinated action across industries, international regulatory bodies, and supply chains. The complexity was daunting, and so the paper joined thousands of others in academic databases, available, documented but not translated into immediate action. In 2015, a documentary filmmaker named Anna Peterson was researching global supply chains for an entirely different project. She was following the journey of everyday objects from raw materials to consumer products. During an interview with Dr. Keller about materials sourcing, he mentioned his 2011 paper. She began reading the technical reports he'd compiled. Anna wasn't an engineer, but she understood how to trace connections. She pulled investigation reports from the disasters Dr. Keller had referenced: Sampoong, Air France 447, Enschede, and others. The Hyatt Regency Walkway collapse in Kansas City, 19. The Aloha Airlines fuselage failure, 1988. The I-35W bridge collapse in Minneapolis, 2007. In each technical appendix, she found the same pattern Dr. Keller had identified: different immediate causes, design errors, maintenance failures, operational mistakes, but stress corrosion cracking appeared repeatedly in the forensic materials analysis sections, and the same material specifications appeared across multiple disasters. She began mapping the supply chain, tracing where these materials originated, how they were specified, who certified them, and where they ended up. What emerged was a vast network. A handful of major steel and alloy manufacturers supplied materials to thousands of fabricators worldwide. Those fabricators produced components for tens of thousands of construction firms, aircraft manufacturers, shipyards, and industrial facilities. Those entities built the infrastructure used by billions of people daily. At the center of this network were the specifications, industry standards, international building codes, aviation regulations, materials certifications. These specifications were developed by committees comprising industry representatives, engineers, regulatory officials, and academic experts. The committees met periodically to review standards based on new research and incident data. The process was designed to be thorough and consensus-driven, which made it inherently slow to change. Anna interviewed retired engineers who had participated in standards development and post-disaster investigations. Most agreed to speak on background, not for attribution. One former investigator who worked on aviation safety assessments told her, "We encounter stress corrosion cracking in routine inspections regularly. We document it, repair it, monitor it. But you can't replace every aircraft component or ground entire fleets for comprehensive materials upgrades without enormous economic disruption. So you do risk management, inspect what you can, replace what shows damage, prioritize based on criticality. The system is built on managing acceptable levels of risk." Another engineer, involved in infrastructure assessment, explained, "When a bridge shows signs of stress corrosion and structural members, we evaluate whether immediate repair is necessary or if continued monitoring is sufficient. We can't rebuild every aging bridge simultaneously. Resources are finite, so we categorize by risk level and allocate maintenance funding accordingly. It's not ideal, but it's the reality of managing vast infrastructure systems with limited budgets." These weren't admissions of wrongdoing. They were descriptions of how complex systems operate in practice, balancing safety priorities against economic and logistical constraints. The engineers weren't indifferent to safety. They were navigating difficult trade-offs inherent in maintaining civilization-scale infrastructure. But the accumulated effect of these individual decisions, made independently across industries and continents, was that known material vulnerabilities remained embedded in critical systems worldwide, not because anyone decided to ignore the problem, but because addressing it comprehensively would require coordinated resources and political will that didn't materialize. Anna's documentary was never completed. Funding challenges. Some potential subjects declined to participate. Legal concerns from some institutions. The project stalled, but her research archive remained. A detailed map of how material specifications used globally in 1995, 2000, and 2009 connected disasters across continents through a shared vulnerability that was documented but not systematically addressed. The connection between Sampoong Air France 44-7 and Enschede is not a conspiracy. It's not a cover-up. It's not even a secret. It's a systemic consequence of how we build our world. In the 1960s and 70s, as globalization accelerated, there was a push to standardize materials and specifications internationally. The goal was laudable: ensure consistent quality, enable global trade, reduce costs through economies of scale. Committees were formed. Standards were written, alloys were tested and certified. These specifications became the backbone of global construction, manufacturing, and engineering. But standardization has a hidden cost. When everyone uses the same material, a flaw in that material becomes a universal vulnerability. When everyone builds to the same minimum specification, there's no redundancy in the system. When everyone optimizes for cost, the margins of safety shrink uniformly. The specific alloys implicated in Sampoong Air France 44-7 and Enschede were chosen because they met international standards for strength, weight, and corrosion resistance. They were tested in controlled conditions. They passed, but the tests didn't account for long-term exposure to combined stress and environmental factors. The tests didn't simulate decades of use. The tests assumed ideal maintenance conditions. In Seoul, the combination of mechanical stress, vibration, and chloride-rich moisture created conditions that accelerated corrosion beyond test parameters. Over the Atlantic, the combination of thermal cycling and atmospheric conditions created conditions that compromised sensor integrity. In Enschede, the combination of mechanical stress and industrial pollutants created conditions that generated ignition sources. These were not unpredictable conditions. They were real-world conditions, but they were outside the test protocols. And here's the critical point: the flaw was known. Materials scientists understood stress corrosion cracking. Engineers encountered it in inspections. Researchers published papers about it, but the knowledge was siloed. The building engineers didn't talk to the aviation engineers. The aviation engineers didn't talk to the industrial safety engineers. Each industry saw stress corrosion cracking as a specific problem in their domain. No one asked, if this alloy is failing in buildings, and failing in aircraft, and failing in industrial equipment. What does that say about the alloy itself? The answer was uncomfortable. It meant that millions of structures, vehicles, and systems built over the past 50 years contained materials with a known vulnerability. It meant that the infrastructure of modern civilization had a distributed fragility, a weakness built into its foundation. Addressing it would require identifying every critical application of vulnerable alloys, assessing the risk based on stress, environment, and age, prioritizing replacements or reinforcements, updating specifications and regulations. The cost would be measured in trillions of dollars, the time would be measured in decades, and the political will to act on a problem that manifests unpredictably was non-existent. So the system continues, inspections are performed, maintenance is scheduled, failures are investigated, and the same materials continue to be specified, manufactured, and installed. Because changing the system would mean admitting the system was flawed. And admitting the system was flawed would mean liability, would mean lawsuits, would mean political consequences. So instead, each failure is treated as an isolated incident. Specific causes are identified, specific correctives are applied, lessons are learned, but the underlying vulnerability remains. In the bridges you cross, in the buildings you work in the planes you fly in the pipes that carry your water, in the tanks that store fuel, in the cranes that build skyscrapers. Right now. Consequences and present risk. 502 people died in Seoul. 228 died over the Atlantic. 22 died in Enschede. These numbers are documented, verified, mourned. But how many others? How many failures attributed to structural fatigue, or material failure, or age-related deterioration were actually stress corrosion cracking? How many near misses were caught just in time? How many incidents were never investigated deeply enough to identify the root cause? In 2019, a pedestrian bridge collapsed in Genoa, Italy. 43 people died. The investigation found corrosion in the steel cables, stress corrosion cracking, the same pattern. In 2021, a residential building collapsed in Surfside, Florida. 98 people died. The investigation found corrosion in the reinforcement, stress corrosion cracking in a chloride-rich coastal environment, the same pattern. These are not isolated incidents. These are symptoms of a systemic vulnerability that exists wherever we used minimum specification materials under real-world conditions. The risk is not uniform. Some structures are more vulnerable than others. Structures built in corrosive environments, coastal areas, industrial zones, areas with road salt, structures under high mechanical stress, tall buildings, long-span bridges, pressurized vessels, structures that have been in service for decades, aging infrastructure worldwide. But identifying which specific structure will fail next is nearly impossible. Stress corrosion cracking is invisible without destructive testing. You can't see it by looking. You have to cut into the material, examine it under microscopes, analyze the grain structure. Comprehensive inspection of all critical infrastructure would require taking structures out of service, performing invasive testing, analyzing results, making decisions about repair or replacement. The economic and logistical challenges are staggering. How do you take a bridge out of service for months of testing when thousands of people depend on it daily? How do you ground an aircraft fleet when the airline industry operates on thin margins? How do you evacuate a building for structural analysis when people live and work there? So instead, we do risk management. We inspect what we can when we can. We look for visible signs of distress. We monitor known problem areas. We hope we catch failures before they become catastrophic. And sometimes we do. In 2016, cracks were discovered in the steel structure of the San Francisco-Oakland Bay Bridge. Stress corrosion cracking, caught during an inspection. Repairs were made. Catastrophe was averted. But the inspection only happened because engineers were specifically looking for problems in a new section of the bridge. How many older structures, built decades ago, are not receiving the same level of scrutiny? In 2020, the National Transportation Safety Board in the United States published a safety recommendation. It called for improved inspection protocols for aging metal structures. It specifically mentioned stress corrosion cracking as an area of concern. The recommendation was noted. Some jurisdictions updated their inspection guidelines. Some increased funding for infrastructure assessment. But systemic reform replacing vulnerable materials, updating specifications requiring higher safety factors did not occur, because the political and economic will does not exist, because the immediate costs are visible and certain, because the benefits are invisible and probabilistic. You can't point to a specific disaster that was prevented. You can only point to disasters that happened, and each time a disaster happens, we investigate. We identify immediate causes. We assign blame. We implement specific correctives. We tell ourselves, this won't happen again, but it does. Different place, different context, same underlying vulnerability. The connection between Seoul, the Atlantic Ocean, and Enschede is not a mystery. It's not hidden. It's documented in technical reports, academic papers, and engineering journals. The connection is this: we built our modern world using materials that were good enough. We standardized those materials globally to reduce costs. We tested them under ideal conditions and assumed they would perform under all conditions. We built to minimum specifications and assumed the margins of safety would hold. And for most structures, most of the time they do. The building stands, the bridge holds, the plane flies, until the specific combination of stress, environment, and time reaches a critical threshold, until the invisible cracks propagate beyond the point of no return, until 20 seconds in Seoul, until 4 minutes over the Atlantic, until one spark in Enschede. The question is not whether there will be another failure. The question is where and when, because the materials are still being used. The specifications are still being met. The system is still operating exactly as designed. Somewhere, right now, a microscopic crack is forming, in a beam under stress, in a sensor cycling through temperature extremes, in a fastener exposed to corrosive air. It's invisible, it's growing, and by the time anyone notices, it will be too late. The signs were there. 1. On June 29, 1995, employees at the Sampung department store heard the building groaning. They reported it. Management dismissed it. Hours later, 502 people were dead. On June 4, 2009, Air France received automated maintenance messages from Flight 447, indicating sensor failures. The messages were noted. The plane was lost. 228 people were dead. On May 13, 2000, workers at the Enschede Fireworks Depot reported issues with container door seals. The issues were acknowledged. The repairs were scheduled. Hours later, 22 people were dead. The signs were there, every time. The warnings existed, in technical reports, in inspection logs, in maintenance records. But the warnings were not connected, not synthesized, not understood as symptoms of a systemic problem. Dr. Heinrich Keller's 2011 paper laid out the pattern. Anna Peterson's research documented the supply chain. Engineering journals published papers on stress corrosion cracking. Professional societies issued recommendations. The knowledge exists. The problem is known. But the response is fragmented, industry by industry, incident by incident, reaction by reaction, because confronting the truth means confronting an uncomfortable reality. We built our civilization on compromised foundations. We chose cost over resilience. We chose efficiency over redundancy. We chose good enough over safe enough. And we continue to make those choices, every day. Every time a specification is written to minimum standards. Every time a material is chosen because it's slightly cheaper. Every time an inspection is delayed because the budget is tight. The invisible flaw is not in the metal. The invisible flaw is in the system. A system that optimizes for short-term economics over long-term resilience. A system that treats safety as a cost to be minimized rather than a priority to be maximized. A system that learns from failures but does not fundamentally change. Somewhere tonight, people are walking across a bridge. The bridge was built 30 years ago. It met all the standards. It passed all the inspections, but invisible cracks are forming in the steel cables. Stress, corrosion, time. Somewhere tonight, people are boarding an aircraft. The aircraft was manufactured a decade ago. It met all the certifications. It passed all the maintenance checks, but microscopic fractures exist in critical components. Stress, environment, cycles. Somewhere tonight, people are sleeping in apartment buildings. The buildings were constructed 20 years ago. They met all the codes. They passed all the assessments. But the reinforcement is corroding invisibly. Stress, moisture, time. The connection between Seoul, the Atlantic, and Enschede is not just about the past, it's about the present. It's about right now. Because the decisions made in boardrooms and on factory floors decades ago, decisions about materials and specifications and costs, are still determining who lives and who dies today. The signs are there. They've always been there. In technical appendices, in inspection reports, in academic papers, waiting for someone to connect them, waiting for someone to act. But systemic change is hard. It's expensive. It's disruptive. It requires admitting that the way we've been doing things is not good enough. And so we wait. We inspect what we can. We repair what we find. We hope we catch the next failure before it becomes catastrophic. We hope. But hope is not a strategy. Hope is not engineering. Hope is what you're left with when you've optimized everything else away. The invisible flaw is not invisible anymore. We know it's there. We know where it is. We know what it does. The question is, what do we do with that knowledge? Do we change the system, or do we wait for the next Seoul, the next Atlantic, the next Enschede? The answer will be written not in technical reports or academic papers. It will be written in steel and concrete, in lives saved or lives lost, in the choices we make about what our civilization is worth. Because somewhere right now, the clock is counting down, the stress is accumulating, the cracks are spreading, the signs are there. And when the next failure comes, and it will come, we will investigate, we will analyze, we will conclude, we will say we learned important lessons. But the real lesson was always there, visible to anyone who looked carefully enough. Connected across continents and decades. Everything was connected. The signs were there all along.